Dense retrieval and keyword search fail in different ways. Milvus hybrid search lets you combine BM25, vectors, and reranking in one RAG pipeline. You'll understand the pattern behind a pipeline that indexes Milvus-ready docs and re-ranks hybrid search context for answers. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Hybrid retrieval matters when a single approach misses half the signals. A company FAQ corpus can contain both conversational answers and dense technical terms. Keyword search finds the jargon. Dense vectors find the paraphrases. The pain point is piecing them together so an LLM gets the best context for its answer. Think of hybrid retrieval like a two-lane road. One lane carries literal matches. The other carries semantic matches. Success is a ranked set that balances both lanes and a small re-rank step to polish the top candidates. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We will build a tiny demo that encodes 3 documents with both sparse and dense signals, pushes them into Milvus, indexes both modalities, runs hybrid search, and re-ranks the top candidates for RAG context. The demo keeps each step minimal, so you can map it to larger data later. This first snippet connects our local process to a lightweight Milvus instance and produces both dense and sparse embeddings from 3 example documents. The snippet shows connections connect to keep Milvus light alive, while BGERerankFunction embedding function use FP16 false device equals CPU emits 2 outputs in one pass, giving dense dim and sparse dim vectors per document. The documents mix conversational lines and jargon, so you see why dense-only retrieval would miss specifics. We stash doc embeddings as a pair of CSR matrix and NDRA, so later inserts and searches can reuse them without re-encoding. The console readout confirms both vector modalities are ready for combined retrieval. Now that we have embeddings, we need a place to store them and avoid schema mistakes that break later pipelines. This snippet gives you a live Milvus-like connection and produces both dense and sparse embeddings for 3C documents via BGERerankFunction embedding function. Engineers worry that dense-only retrieval will miss jargon, so docs mixes colloquial and term-heavy phrasing to surface the pain point. The call to connections.connect keeps a lightweight Milvus runtime alive, while BGERerankFunction embedding function use FP16 false device equals CPU emits both dense dim and sparse dim from a single pass, preserving latency budgets. We stash doc embeddings for reuse, so every later insert or search can slice the CSR sparse matrix and NDRA without re-encoding. The console readout confirms both vector modalities are ready for combined retrieval. With embeddings stored, we must create a collection with the right fields so Milvus accepts both modalities and text for later re-ranking. This example creates the Milvus collection schema and inserts our hybrid vectors so later queries have both signals to work with. Missing a text column or sparse field is where many pipelines break, so field schema entries explicitly reserve room for text, sparse float vector, and float vector data types. Collection hybrid demo schema consistency level bounded reuses the connection from step 1 and lets Milvus auto ID rows, while call insert pushes the docs alongside their CSR matrix and NDRA payloads. Because we drop any stale collection before recreating it, we avoid duplicate vectors during experiments. The inserted rows counter shows the store now holds every document we'll query later. Indexes make search fast and change the nature of results, so we must add the right index types before comparing routes. This code builds the indexes, loads the collection, and surfaces how dense and sparse searches differ in practice. Without these create index calls, sparse vec queries default to a slow scan, so we explicitly add sparse inverted index and auto index before calling call.load. The shared params dict keeps metric type consistent, while call.search runs once with query dense and once with query sparse to surface their different matches. Dense retrieval leans on semantic overlap, whereas the sparse path favors literal terms like Milvus. So seeing distinct fragments in the output tells us why hybridization matters. The printout highlights which approach wins the top slot for this query. Hand-merging results by code is fragile. Instead, we ask Milvus to blend scores so we can tune the balance between literal and semantic hits. This snippet fuses the two retrieval routes with Milvus-WeightedRanker to produce hybrid hits that combine literal and semantic signals. An search request wraps the dense vec and sparse vec searches, so call.hybridsearch.ack can re-rank them together instead of stitching results manually. WeightedRanker, sparse weight, dense weight, normalizes both score scales and then blends them, giving us a tunable bias knob between exact term matches and semantic recall. Raising sparse weight pushes jargon-heavy hits upward, while decreasing it favors the embedding lane, so you can tailor the balance per application. The printed weights line confirms the fusion ran and shows the top document after weighting. Finally, we take the small hybrid candidate list and give a cross-encoder a quick re-rank to produce precise RAG context. This example applies Milvus BGERerankFunction to rescore the hybrid candidates and produce a concise context for a generator. Cross-encoder re-ranking is expensive, so we feed it only the small candidate texts list returned from hybrid hits to keep latency manageable. BGERerankFunction, model name BAAI BGEReranker base, device CPU, runs locally, yet still yields calibrated scores, and the slicing into top K texts builds a concise answer context. If you increase the slice beyond 2 snippets, you gain recall at the cost of longer prompts. Trimming it tight preserves downstream model focus. The CTX preview line shows the leading excerpt and its confidence for the final generation step. This toy flow maps directly to real systems. Swap the 3 docs for a company's 1,000-page knowledge base. Keep the same steps, but add batching, async inserts, and an ANN index for scale. The pattern stays the same. Dual encoding, explicit schema, proper indexes, weighted fusion, and cheap re-rank on a small candidate set. This wrap-up, in plain words, we store both sparse and dense vectors, blend their scores to balance literal and semantic matches, then re-rank the top few candidates so an LLM sees sharper context. Use this when your data mixes jargon and paraphrase and you need both kinds of recall. One caveat: re-ranking tightens precision, but adds latency, so only re-rank a small candidate list. Next step, tune the sparse weight versus dense weight in WeightedRanker to match your precision recall trade-off. Or try a larger top K before re-ranking to test recall gains. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.